Hello everyone, welcome back. We shall proceed with our inspiring talks. Stanko Kuveljic, our next speaker, is a data scientist at Market, where he works on both data science and data engineering projects, mostly using Apache Spark and TensorFlow. Stanko will talk about segmentation and classification of time-lapse embryo videos in vitro fertilization using deep learning. We would deep dive into several neural networks architectures that are used in this interesting project. So Stanko, the microphone is yours.
Hi, I'm Stanko, and today we're gonna talk about something. Today we're gonna talk about how can we use deep learning to help doctors to choose the best embryo in vitro fertilization. Best embryo is the embryo which has the highest chance of implanting, which means highest chance in resulting to liveborn baby. There is some information about me. There are contact points, so if you need anything, if you have any questions, if you need any materials about deep learning, you can always message me. And pretty much these pictures are me. I read manga, watch anime, play games. I like cats. These two are my cats. Orange one is Azrael, and black one is Gigi. Also, if you want to play games with me, add me on Battle.net. And I'm afraid we won't have time for questions. And you can always come to me after a presentation, or find me, or message me, or whatever you like. So let's start. These are our quests for today. First, we will start with why we are doing this and what is this. And then we're gonna talk about one big neural network architecture that I used. And also we're gonna deep dive into each sub-architecture of this big architecture. At the end, we will finish so much quest and we will gonna level up. And after that, I have one special quest for you. So I won't gonna talk about what are neural nets, what are convolutional neural nets, RNNs, batch normalization. I assume you already know that, so I won't lose time for this. And in vitro fertilization, doctors often transfer multiple embryos into mother in order to achieve highest chance of at least one succeeds. But quite often, every embryo succeeds, and then mother ends up with having multiple children. Which is not bad, but some parents want only one child, and some parents don't have resources to raise multiple children. And but this is not a big problem. The major problem is health issues. And the mother that is having multiple children, there are quite risk for death, both mother and children. So there is a law in some countries in European Union that limits how much embryos doctors can transfer into mother at a time. So doctors must choose one embryo that has the highest chance of succeeding. So doctors look at the pictures of videos about early stage embryo developing from first day until first 5 days, and then they use some metrics like shape of the embryo, dimension, time when embryo were cell divided, etc., etc. And with labeled data, with labeled videos, we can train some machine learning algorithm that could help doctors, not to replace, but to help doctors to give final decision. Basically, we choose to use deep learning because we already know that results it gave in a few years ago are quite good, and deep learning is in every sphere of machine learning. For example, it achieved great results in computer vision, in object recognition, detection, face detection, face recognition, in some medical images analysis, in text processing, etc. And what it makes deep learning great is that it can take advantage of a big data. So if data are big, then neural network can perform much better than other traditional machine learning algorithms. But also, big data makes neural networks downfall, because in order to train something meaningful, you need big data, and big data is not always available. So this is it worked. This is architecture that we used in this project. It as input it takes video of first 5 days of embryo development. That is time-lapse video, and every image is shot after 20 minutes, I think. And then after that, those frames are, each frame is transferred to next stage in pipeline, which wants to find embryo on that frame, to center it and prepare it for another stage, which is feature extractor. After feature extractor, we got some feature vector, and the thing that is taking all sequence into account is some RNN, which takes feature vector on frame 1, feature vector on frame 2, etc. And then after that, its output it can be probability distribution or another some feature vector that take whole video into account. And what things that is cool that we want to do is to add several data sources, like we want to add some features about mother, for example age, and another handcrafted feature about embryo. So neural network can take all of that information and it will produce better results. So output of this architecture is probability distribution for 3 classes. One class is liveborn, second is miscarriage, and third one is no implantation at all. So first module is about extracting embryo from the image. Yes, this is example of one frame. There is embryo, there is dish, and there is embryo in it. Embryo could be anywhere in this dish. And sure, we can route that frame into neural network for feature extraction, but we didn't have so much data, so it's better to prepare data and say, hey, embryo will be always in the middle, it will be without noise, etc., etc. So idea is to find some binary mask that would crop this embryo from the image, and then it would be pre-processed for later inputs. First, we tried OpenCV. We tried some basics, brightness correction, and some binarization, error deletion, etc. And with some region of interest selection, we possibly get embryo from the image. But the problem with this approach is that it won't work on every single case that we have. And we have very limited data set, so we wanted some perfect results. And this is not perfect. Like, dude, there is not even embryo on this image. And another problem with OpenCV, and I really hated that, is that you have a lot of parameters and you change small thing and you got cool results on one video. And then same parameters don't work at all on the second video. Well, okay. But we used OpenCV to make a label data set for our first side quest today, UNET. We used OpenCV to create labeled images. Like on the one hand, we have embryos, raw embryo images. And on the other hand, which is label, we have binary mask for that embryo. And we wanted to train neural net to learn to map from this raw image to make binary mask. And UNets are good because they need a very small data set to train well. And basically, it is an autoencoder. So we have encoder part, which has several convolutional layers, then followed by max pooling to reduce dimension, and then again several convolutional layers, then followed by max pooling, etc., etc. And this is feature extractor. After that, we want to from these features, we want to make same sized image, but only binary mask. And the way we're gonna do this, we take these features and do some upsampling by the convolutional layers. So again, we upsample with the convolution, then do some convolutional layers, and again until we get same image size, but with this binary mask. One thing, there are two things which makes UNet cool. First thing is that it is fully convolutional. So we can train UNet on 200 by 200 size images, and then after training, we can apply. We can bring to input 1000 by 1000 image, and it will work great. So this is first thing. And second thing which makes UNet cool is that it has this skip connection. It directly transfers output from convolutional layers into later decoder layers and concatenates it. So this is cool. We have directly information transfer, and in the training time, when gradients are calculated, and they are back propagating to the network, but also it will skip right here. And gradients, when comes, there is possibility that gradient that is going through whole network, it will be lost there. And with this skip connections, we propagate gradient right to the beginning. We used 256 by 256 random crops from labeled embryo images. Then we done some data augmentation, like random rotation, translation, vertical flip, horizontal flip, adding some noise, etc. As long as we add the same augmentation on the labels, on the label, binary max, we were good. And results are much greater than almost perfect and much better than OpenCV. We used some standard DEC convolutional filters, 3x3, use activation rel, batch normalization, and now when this is trained, we can apply this binary mask on frame, extract embryo, center it on the image, normalize image, and then this image is ready to do in feature extractor. Or whatever. So, we choose the unsupervised feature. We used unsupervised feature extraction technique because we have both labeled and unlabeled videos. So we want to take advantage of all unlabeled videos. Unsupervised feature extractor don't require labeled data. So we use as input, we will bring some pre-processed embryo, and as output, we will get some feature vector that's representing this input. And we implement these two things. One is variational autoencoder, and second one is stack denoising autoencoder. We also wanted to try GANs, but didn't have time. So this is some future works. So second side quest is variational autoencoder. Basically, variational autoencoder is just like the plain old autoencoder. It has encoder part, which takes an input image and tries to extract features, and outputs some feature vector. And then, which is a smaller representation of input. And then the decoder network takes that feature vector and tries to reconstruct back this input image from only this feature vector. What is bad with plain old autoencoders that these features extracted are so much diverse. For example, one value can be -100, second value can be 1000, etc., etc., and with some gibberish in the middle. So what does variational autoencoder do? Is it tries to fit input data into normal distribution. So by fitting these two networks inside it, it have mean fully connection network and standard deviation, and by combining those two, it enforces a network to fit features into normal distribution. Also, in encoder network, we can use convolutional layers, batch normalization. We can use skip connections. It is no matter, but we must have this part. And I can say that variational autoencoders are pain in ass to train. I trained so many times, and each time I have headache about it. It's so parameter dependent how you can set up these things, and when you train it after a long time, you see this shit for real. And second side quest of autoencoders is stack denoising autoencoder. So this is basically the same like all autoencoders, but it trains differently. It trains layer by layer. So, for example, here we have first layer which have input image, one encoder layer, one decoder layer, and it reconstructs output image. And it trains. Only this one layer it trains, back and forth, which achieve that this layer is forced to learn some low features like edges, colors, etc. And next, when we train one layer, next goes second layer. We freeze this one layer, and we also make one convolutional layer which takes an input from this feature vector from layer 1, and then we also train one decoder layer which tends to reconstruct again this feature vector from layer 1. And then when we're done with layer 2, we go to the layer 3, 4, 5, any layer we want. And there are two things that are worth mentioning here is that denoising part, which means at the input of each layer, we are adding some noise, some corruption, and we enforce this layer to reconstruct image without this corruption. For example, we add some black and white pixels to image, and as a reconstruction, we must not see these black and white pixels. And second thing that speed up training an autoencoder is tide weights. So we use basically the same weights for convolutional and deconvolutional layer, and that doesn't take it takes less memory, and it speed up training. Now there are results. As I said, the stack denoising autoencoder for the same architecture and same amount of training, stack denoising autoencoder was much better, and because it's slowly, layer by layer, trained to extract some feature. For example, first layer it was edges, second layer it was some basic textures, next layer was some shapes, etc. And variational autoencoder needs a lot more training, and it tends to produce some blurry images. So we stick with stack denoising autoencoder. And this is filters from stack denoising autoencoder. This is filters from the first layer, and we can see the network isn't fully converged, but we can see some vertical edges, horizontal edges, diagonals, some black and white changes, etc. Now we are ready to classify the whole video. We have a part that take embryo from the frame, it's pre-process it, then we put that embryo to the feature extractor to get some feature vector, and then we can input this feature vector into some RNN, which will do some classification. So outputs of this video classification was whether state vector, if you want to use some external data sources, or probability. We try liveborn, miscarriage, and no implantation classification, but we realized that liveborn and miscarriage are a lot similar, and it is hard for network to distinguish between those two. So we make two new classes, which is implant and no implant. Also, one problem with video classification is that videos are really high, and there is a large number of frames, and sure, we can put all those frames into LSTM, but we didn't. But you need to have big data, and you need a large data set, and also you need a much greater amount of resources and time to train this thing, and it's prone to overfitting. So we decided to For example, we decided to do some downsampling. And by that, I mean we took all frames from the video, and then we divided those frames by, for example, 100. Now we have 100 groups of the frames, and then we sample from each group one frame, and that way we make another video with 100 frames. So this is also a technique that we can sample as many times as we want, and then this is some kind of data augmentation as well. And it proves to work okay. So this is basically that I said earlier. There is some pre-processed embryos from UNETs. Frame 1 going to feature extraction part. Then after it gets its feature vector embeddings, it goes to the multi-layered LSTM network. Next, going frame 2, it goes to feature extractor part. Its feature vector goes to LSTM network, and etc., etc., until we hit the end, and at the end we got some probability distribution. So we used basically 2 to 3 layers and in this LSTM, about 500 to 1,000 units with some dropout. We augmented data set both with image augmentation and with augmentation from downsampling. So, but image augmentation, it must be same applied to whole video. And one good thing that this feature extraction is frozen. So in a training time, it won't train. It trains only this LSTM network. But with much bigger data set and with much more resources, we can unfroze this feature extraction. And this will be fine-tuning. And now our neural network would train both LSTM, and gradients will be propagated down to convolutional neural networks. And this with more time to train and much larger data set, it will produce much better results. Congratulations, we leveled up. We finished several quests. And basically what we have done, we split train and test set. We trained UNET, which tends to extract embryo from the image, and after some pre-processing, we trained stack denoising autoencoder with several layers, and the output of the autoencoder is transferred to LSTM. Then we train LSTM neural network, and after that there comes softmax layer. The training took this amount of time. These are accuracy we got. There are some shortcomings that we need much bigger data set in order to produce better results, and we need more diverse embryo videos. For example, almost all videos were good-looking embryos. So that means that this was almost all embryos that are transferred into mother. So doctor looked at this video and said, hey, it's okay embryo, we can transfer it. And from these embryo videos, we got liveborn, miscarriage, and no implantation. So for future works, we need to collect more data, and we need to explore some other approaches regarding RNNs. We can even try 3D CNNs. I never tried it before, but sure, why not? We can explore some different feature extraction techniques. And as a bonus, this is most interesting part, is to make one end-to-end solution which will take embryo video, it will process it, and then it will take additional information about that video. For example, some patient records and some handcrafted embryos features to let neural network to look at all this and make the best decision. And this is a final quest for you. So if you are interested, SmartCat is hiring. We need some data scientists and data engineers. So if you want to be part of the team, message me or Nenad or someone. And thank you.
Yeah, we still have 3 or 4 minutes and 4 questions, so maybe you would like to answer them.
Okay.
They're quick. Which GPU do you use?
NVIDIA 1050.
Would you share some accuracy metrics on your system?
I wrote down this only accuracy, but there are other metrics which are here, that precision, recall, etc. I don't remember all these. They're not in my head right now.
Is it an open product, and is it possible for everyone to use it for free or not?
No, this is a data set from private clinic.
Where do you get input data? How easy is it?
I'll already answer that.
Yeah. Any plans for venturing outside of the A1 group with these tools?
I don't know. I'm a simple data scientist. I see data, I put my machine learning, and this is all that I know.
How many samples did you had in the data set?
There was labeled videos, there were few thousands, and unlabeled there were much more.
That's all from the platform, so does anyone maybe have any, yeah?
Do you think there are any ethical issues about an AI deciding which embryo gets?
The idea is this to only help doctors. Doctors should always have the final decision, and it will look at the video, it will look at what neural network said, and look at other data sources, and with some intuition it will say, hey, this embryo is from transfer, this embryo is not. This is just some decision support tool.
Any more questions? If not, an applause. Yeah, and something.